Good morning, everyone. Welcome to Search Solutions tutorial session. I'm Haiming Liu. I'm from University of Bedfordshire. I'm the chair of the tutorial. Just have a quick introduction to our tutors, and then I will pass the floor to them. Search Solutions, I don't know whether you participated before, is organized by the BCS Information Retrieval Specialist Group and has been carrying on for decades, more than decades now. And the Search Solution tutorial started in 2011. It's just like often the day before the main event and as a warm-up kickoff event, if you like. And we had the tutorials covered from the common topic on the state of arts of the interest to both academics and practitioners. And because this event is in an effort to bring the academics and the practitioners together and to share academia and also industry experiences. So the topics they're sharing is very relevant to all of us. Today, similarly, we got experienced tutors, Alex, Miguel, John, and Dale. So welcome to all of you. And I pass the stage to you and for you to introduce yourselves. Welcome. Thank you.
Thank you very much. Thanks for the introduction. Hi, my name's, I'm John Reed. So we're here to give this reinforcement learning for information retrieval tutorial. And we'll get underway. So we all work at Blue Prism AI Labs, Alex, Miguel, myself, and Del. So just as a point of order, I guess, we've created a small website for the tutorial. So that's got all the information that you are going to need today, and the URL's there at the bottom of this slide. Okay, I'm going to hand over to Del. He's going to give a little bit of the motivation about information retrieval.
Yeah, hi, good morning. So just a few words about the motivation of this tutorial. Why do I want to talk about the reinforcement learning for information retrieval? First of all, reinforcement learning is really hot nowadays. I'm sure that you have heard of the great successes of reinforcement learning, particularly when it is combined with deep neural networks, for example, AlphaGo, AlphaZero, and so on and so forth. And more importantly, the reinforcement learning framework is very general and very flexible. For example, if you talk about search, using reinforcement learning, it is easy to go beyond the independence relevance judgments, and you can take into account the ranking positions of documents and interdependencies of documents easily in a principled approach. And it's not surprising that nowadays a lot of research papers are making use of reinforcement learning techniques. Just in CKR this year, there are nearly 50 papers mentioning reinforcement learning. And on the other side, we also have the demand pool. So more and more information retrieval applications are provided as web applications or mobile applications. And these applications are personalized and interactive. So for such applications of information retrieval, including search, recommendation, and advertising, we usually have user profiles, and the information retrieval service providers would be interested in optimizing not just the static user preferences, but also try to capture the evolving dynamic user interests. And moreover, they want to satisfy not just the immediate user information needs, but also to engage the user for a long term. So these are some good reasons for us to look into reinforcement learning for information retrieval. Now I'm going to pass to John, who is going to introduce you to the fundamentals of reinforcement learning.
Okay, thanks, Dale. Yeah, so we've got our first session is we're going to talk about reinforcement learning basics, go over some of the key elements and characteristics of reinforcement learning. Yeah, I'll kick off. Okay, so where does, how can we set the scene really? I mean, so modern machine learning, I guess there's three established pillars to modern machine learning. There's supervised learning, unsupervised learning, and reinforcement learning. Yeah, so in supervised learning, we're explicitly providing some sort of teaching signal. We're saying what's right and wrong about potential outputs of our model. Unsupervised learning is really at the other end of the spectrum. So there we've got well-defined data, but no teaching signal. There's no right or wrong. We're just really looking for patterns in the data. Reinforcement learning sits apart from both of those. Here we're learning through interaction with the environment and some sort of reward signal that it provides to us. Right and wrong is not provided explicitly, but it's just provided implicitly through these rewards. So we don't know whether we took the right action or not. All we know is that at some point we got a reward, and we need to associate that with our behavior. Okay, so what is reinforcement learning? Well, really, it's learning what to do. And this really involves mapping situations to actions whilst we're maximizing rewards. So in its most basic form, you can see at the bottom there that RL, reinforcement learning, or RL, involves some interaction between an agent and an environment. The agent is going to act on the environment. It's going to choose what action to perform. The environment is going to update its internal state and provide some information about that back to the agent. At the same time, it's going to provide a reward signal. And this is an ongoing iterative process. So this doesn't just happen once, it can happen an arbitrary number of times. So what comprises reinforcement learning? We're trying to make this a little bit more explicit. So obviously we've got the agent, that is the learning agent. We've got the environment, which is the system that the agent interacts with. This could be a real world environment or a simulation in a computer. The agent has a policy. This defines the agent's behavior, and this is what we want to update during learning. This could be stochastic or deterministic. There's a lot of different ways of defining policies. The reward signal comes from the environment, and the agent is going to use these signals to understand how well it is doing. We've got to recognize that the reward signal is an immediate signal, so it's localized in time. So the agent's goal isn't to maximize any one reward, it's to maximize the total reward in the long run. And that's kind of where the value function comes in. So the value function is specifying what is good in the long run. That is, given a state, what rewards the agent could expect to accumulate in the long run. And then optionally at the bottom, sometimes we have a model of the environment. So this is optional, but it helps. So if the agent understands how the environment works, typically it can perform some sort of planning to optimize its behavior. But there's also, that's called model-based RL. But there's also model-free RL. And this is where the agent doesn't understand anything about the environment. So that's a harder setting, but it's kind of more general. If you have a model-free algorithm, you can apply it to more environments. Okay, so those are the elements, but what are some of the defining characteristics of reinforcement learning? So we're going to discuss them here in a qualitative way. We'll make them more precise later on. So almost always there's some idea of trial and error search. So the agent typically starts with very little prior knowledge and maybe a random policy. So it needs to do experiment to discover what is good behavior, what is a good policy. And that leads naturally on to this idea of exploration versus exploitation. So you can see the trial and error is necessary to improve upon an initial random policy. But what about a bit later on, once the agent has learned some amount of good behavior? Should it continue to experiment to discover even better behavior? Or perhaps it should exploit the good behavior that is already learned to maximize the rewards. So typically there's some sort of tension between those two goals, and some sort of compromise has to be reached there, and that's the trade-off. Delayed rewards. So in a lot of environments, there's this difficulty of delayed rewards. And here we're talking about, we want to estimate the value of a state. We want to know how many rewards we can expect in the long run. But when the signal we get from the reward signal that we get may not happen at the same time that we choose the action that causes that reward. And this can cause difficulties in learning. Typically, in a lot of environments, we have sparse rewards as well, where rewards are only really provided at the end of the task, and we have to figure out what actions we took a long time earlier that resulted in those rewards. So one difference between supervised and unsupervised learning is that typically reinforcement learning, we're going to consider the whole problem. We're going to try and solve a goal that is the goal that we're interested in. In supervised and unsupervised learning, we may use these models as components of a larger system that satisfies a goal, but in reinforcement learning, we're typically considering the whole problem. And I should also mention there's this distinction between on and off policy learning. So I guess on policy is more typical, and this is where the agent interacts with the environment and learns using data generated from that interaction. But there's also off policy learning, and here we may have some other agent or a human, maybe learning from demonstration. There's some other interaction with the environment that produces data, and the agent is tasked with learning from this data. So that's a more difficult task because the agent can't, the experimentation element is reduced because the agent can only work with the data that it has. Okay, so that's, so we can get a bit more into the details now. So most reinforcement learning systems can be put in this Markov decision process framework. And we've got a cartoon here that represents it. So the graph, the states are represented by the green S0, excuse me, S0, S1, and S2 nodes. And when in any state, the agent can take one of two actions, A0 or A1. So given a state and an action, there are probabilities marked on the graph describing the likelihood of a transition to subsequent states. What is a Markov decision process technically? Well, it's a discrete time stochastic control process. And what does that mean? Well, the discrete time means that we've got sequential discrete interactions with the environment. So we're moving from one state to another in a discrete way. Stochastic, we've got this uncertain environment, so there's probabilities associated with the transitions between states, and they depend on the actions. It's a control process because the agent is acting on the environment and choosing what actions to take. And it's Markov because the Markov assumption is encoded here. And the Markov assumption states that you only need to know the current state. If you know which state you're in, the history of the states that you were in does not matter. The process behaves the same. So this is normally a simplifying assumption in most environments, but often, it's all you need to get a reinforcement learning algorithm to work. Oh, and I should say there's an extension here. There's a sort of partial observability extension. So they're POMDPs, and here, the agent isn't aware of what state it's in. It only sees reward signals, and it has to sort of infer where it is in this decision process. Okay, so back to interactions with the environment. So going back to this, this figure that we had earlier, we'll just fill in a few more details. So we know that the agent interacts with the environment by choosing actions, and the environment updates and gives states and rewards. But how does this work in detail? So, we've signified let's start at the top. So the agent is given some state st, time t, and we have a policy pi. So the agent's behavior is defined by this policy. So this could be a stochastic policy, it could be a distribution, probability distribution. So we're drawing an action from this policy. We're applying this action to the environment. And then internally in the environment, the environment is updating its state according to some probability distribution that depends on the state and the action. And it's also generating a reward that can depend on the state, the action, and the subsequent state. But the agent may not necessarily see or understand how this works. And that's, again, the difference between model-based and model-free RL. And then, of course, as we know, the state and the reward gets passed back to the agent, and this iterates. And that's what's known as a trajectory, or a rollout, or an episode. And this is a sequence of tuples, really, state, action, reward tuples. And it's from these episode and rollouts that the agent will be learning. Okay, so the credit assignment problem is a well-known problem that's at the heart of a lot of the difficulties in RL. And I think we briefly mentioned this earlier, but here's a more concrete example. So really here we're asking which actions led to a reward, and this isn't obvious for delayed or sparse rewards. So if we look at the cartoon, we can see that there's two rewards. So at the top, there's a +5 reward coming from the transition between S1 and S0 via action A0. And there's a -1, so a negative reward coming from the transition between S2 and S0 via action A1. So if you like, what we'd like to do is to assign positive credit to any actions that result in this +5 reward, and negative credit to actions that result in this negative reward. But if you look at state S2 and action A1, quite often it's going to lead to this negative reward. So maybe that's easy to identify. If we look at the +5 reward at the top of the cartoon, it's a little bit more difficult. But if you trace back in the graph, you can see that actually you need to take the same action A1 in state S2 to arrive at that +5 reward. So it's that difficulty of associating the necessity of action A1 in state S2 to achieve a good reward that makes this credit assignment problem hard. And that really is what a lot of these reinforcement learning algorithms are trying to overcome. Okay, so rewards and returns. So for the moment, we've just spoken about rewards localized in time. And we've spoken about this value function, which is how many rewards we expect to get in the long run. That is also defined as a return, right? So the return is a sort of cumulative reward in the long run, and it's defined as a sum, as a weighted sum over all the rewards you get for a particular episode. So we can see on the right that we've got two different forms here. We've got an infinite horizon discounted return. So this is where we look infinitely far into the future, but we discount all the rewards in the future with this gamma discounting factor. Or an alternative is just to look to finite horizon, just a set number of steps into the future and not do any discounting. You can make a combination of both, but they tend not to work well in practice. If you have an infinite horizon with no discounting, there's no incentive for the agent to, if you're trying to maximize your return, there's no incentive for the agent to gather any rewards anytime soon. So quite often you find that the agent doesn't feel any urgency in solving the task, which is not typically what you're after. Okay, so I mean, we're going to start talking about value-based methods. So I just thought I'd stop here and ask if there's any questions before I go on. No? Okay, good. All right, so here we've got value-based methods. So in this session, we're going to discuss these. These are methods that estimate the value function directly. There are other reinforcement learning methods, such as policy gradient, that optimize the policy directly without estimating this value function. And they're going to be introduced in later sessions. So we know the value function describes the worth of being in a state, or perhaps of being in a state and taking some action. These are these V and Q functions respectively on this slide. We can see here that these are expectations of returns, right? So the returns is the discounted rewards in the long run. Once we have defined our returns, infinite horizon discounted or finite horizon undiscounted, we're interested in choosing our policy pi so as to maximize an expectation. And this expectation is really, we're sampling, so these tau in the expectation are samples, are episodes that are sampled from our behavior pi. But there's also possibly uncertainty in the environment. So we should see these expectations as being over any distribution that the environment introduces onto these episodes. So yeah, and we should be clear that this V function is an estimate of the value of the state, right? And that's different from the Q function, where we're trying to estimate the value of taking a particular action A in a state S. So we're gonna look at this distinction in a bit more detail. Okay, so here's a starter reinforcement learning environment that we're going to experiment with. There's a frozen lake that you have unfortunately lost your frisbee on. Worse still, the ice is slippery and movement on the lake is uncertain, so you don't always end up going where you want to go. Even worse, there are holes in the lake that you can fall into. Now you might say, oh, well, it's only a frisbee. Perhaps it would be wise to leave it on the lake and not risk your life. But it turns out there's an international frisbee shortage and you must retrieve your disc. So in the grid, we can see the rewards for arriving at the terminal states. So these are the whole states and the goal state. So the reward is +1 for the goal and -1 for the holes. Our task is really to learn how to navigate from the start state to the goal. So how can we do this in a state value setting? So one way, if we had an estimate of the value function for each state, perhaps we could choose which way to go by looking at the neighboring states and choosing the one with the highest value. That would go some way to defining that policy to control navigation across this lake. And you can imagine that this would work quite well in this setting where the numbers on the slide represent our estimates of the V value function. But we're going to make life a little more complicated for ourselves. We know that this model-free setting of RL is more general than model-based, so we're going to consider that for a moment. So here we really don't know anything about how the environment works and how does that manifest itself. In particular, we don't know which state we're likely to end up in after taking a particular action. So what are we going to do when we're in this highlighted state? As we said before with the value function, the naive view is we would just choose to go down because down has got the highest value down here. But in the model-free setting, of course, we cannot do that. And this is the motivation for Q learning. So instead of estimating this value function, we're going to estimate the state action Q value function. And perhaps you can see with this example why this is a very general form of reinforcement learning, as it is model-free. We've got one slide with a slightly different environment, just to compare to when you might use model-based reinforcement learning. Yeah, so a typical setup for model-based reinforcement learning would be board games, and model-based RL is very often used in these environments. So here, the model of the environment is really the game tree, right? Each node in the game tree is a state, and the environment can only go between states that represent legal moves in the game. And here we've got tic-tac-toe as an example. Now, if the agent knows how the game works, obviously it can do some planning using this game tree. So alpha, it's I think the typical examples for game playing would be a minimax search over the game tree with, there's all these specialist approaches like alpha beta pruning and Monte Carlo tree search that you hear methods like AlphaGo using. Now, what I would say is that this obviously makes the problem a bit easier because you're encoding domain knowledge into the agent, but it makes the agent domain specific, right? The algorithm to teach the agent depends upon the form of the environment. Okay, so back to our model-free frozen lake environment. So here we've expanded what we're estimating. We're not estimating the value function anymore. We're estimating the Q-value state action function. So for each state, we've got an estimate of the value of taking any one action. So if we're in the start state, we've got an estimate of the value of going right. Yeah, and you can see here that our estimates are pretty reasonable, actually. So to go, our estimate of the value of going down from this state, the second state, into the hole be minus 0.9. And you can imagine if we had these estimates of the state action Q value function, it'd be quite easy to define a policy that had a reasonable chance of ending up at a goal. So what would that policy look like? Well, the simplest policy would be to take the best estimated action for the current state. So we've got the same numbers here, and we just highlighted them in red. So how would that work? At the start, we'd identify there are two states with the same value, and we'd probably just break that tie randomly, and we could navigate through this frozen lake environment. The problem is, how do we get to a situation where we've estimated these Q values well? And that's where Q learning and temporal difference learning come in. So Q learning is a value-based algorithm, and it's going to estimate this Q value state action, function that we've spoken about. One thing to note is that we need an environment with discrete actions in order to be able to take this argmax to define our policy. So that's an assumption that we need a discrete action space. Once we've got that, however, we can employ this method called temporal difference learning to learn this Q value function. And how does that work? Well, really, if we recognize that we start with a random Q estimate, we need some way to improve it given our experience of interacting with the environment. And how's that going to happen? Well, whenever we get a reward signal, that's essentially going to give us some idea about how valuable that current state is. But the reward is not the only component of the value of that state. There's also the state that we're going to, the subsequent state that we're going to move into has a value. So this forms this TD target component here. So we've got this RT, which is the current reward, and then we're going to discount our current estimate of the subsequent state. And we're going to argue that given the current reward, this is a good estimate for the value of our current state. However, we shouldn't forget what we've already learned, which is already encoded in our Q value function. So this will be a noisy estimate of the Q value function. So we're going to take our new information here in the TD target. We're going to form the TD residual by taking the difference with our current estimate of the value. And we're going to update our current estimate of the value by that difference, but multiplied by some learning rate. So this learning rate can vary between 0 and 1. If it's 0, there's going to be no learning. If it's 1, we're always going to overwrite our estimate of the Q value with our new information here. So typically you want to set this to some smallish value close to 0. And the idea is that as we do this, as we iterate over all these episodes that we can generate through interacting with our environment, is that this Q value estimate is going to get better and better. And once we've got better estimates, our policy is going to behave better, and we've got higher chances of reaching the goal. And there's a theoretical justification for that. So you might have heard of the Bellman Equation. So this applies when we're using these infinite horizon discounted returns. So remember, we've got this gamma discounting factor, and we're looking infinitely far into the future. And really, because we've got this definition of the V value function of a state, is just the expectation over rollouts of the return. It's easy to see that you can break this. You can break the first term of this return's infinite sum. So you take this R0 out of the sum, and then the remainder of the sum is actually just the value function applied to the subsequent state discounted by gamma. So there's this recursive nature to these infinite horizon discounted returns. So now we see that if we want to estimate the value function for state S0, an unbiased estimator would be the expectation of the reward at time 0 plus gamma times V, the value function at the subsequent state. And that's really what inspires temporal difference learning. Because if we go back to the slide here, we can see that this max Q, we know that this is the value function V, because this is the value of the state is simply the value of us taking the best action in that state. So this matches exactly the policy pi. So we've got a discounted V, gamma times V plus RT, which is exactly what we see in this Bellman equation. So the Bellman equation is telling us that this is an unbiased estimator, this TD target, and then we're just going to use this unbiased estimator to update our current estimate. Okay, so those are the equations. How does it work in practice? Well, the simplest form of Q-learning is really tabular Q-learning, and that's we're going to estimate these values by storing them individually in the table. So here we need 4 values for each state, representing each of the 4 possible actions we can take in that state, and we're going to do that for each state in the game, barring maybe the terminal states. No, we need to include the terminal states, but okay. All right, there's a couple of other points that can trip us up, so let's discuss them quickly before we go into an exercise. So let's imagine what happens early in learning. So here we've got, if we imagine we've already established these state action estimates on the slide, what behavior is going to result. And here the question marks indicate that we haven't really tried, we haven't explored that state and action pair. So we've got no idea what the Q value function should be for that state action pair. So the behavior really depends. So you can see we're going to start in the start state and we're going to choose each action with the same probability, right? So say we go right. So I should say if you choose up, you just come back to the start state. That's how the environment works. But say we choose right and we go to the right here. Now we're in the state and we know coming back is probably about a 0 and going down is a -1. So if we choose not to explore unexplored state action pairs, we're always going to be stuck in this repetitive behavior where we go back and forth. So it's obvious here that some sort of exploration is necessary. And what do? There's a couple of approaches we can use to break out of this local minima. One simple approach is whenever we identify there's a state action pair we've never tried, is just immediately explore it. Another approach is just to have some parameter that determines how often you choose a totally random action instead of an action from the policy. And that will obviously encourage exploration as well. This is early on in learning. So like I said earlier, if later on in learning, when we've got good estimates, we probably don't want to explore too much because we want to take advantage of the strengths of the current policy for acquiring rewards. If we explore too much, our return is going to be lower. And we're going to find that we're going to have to tune this compromise, this trade-off between exploration and exploitation in our reinforcement learning algorithms. And that's probably going to be quite environment dependent. Okay, another thing I should mention is that Frozen Lake is it's a well-defined benchmark environment. So it's a lot of people write reinforcement learning algorithms to see how well they do on Frozen Lake. And in the environment that's established as a benchmark, the holes aren't actually given a negative reward signal of -1. The holes in the real environment are 0. And this can cause some problems during learning regarding exploration, right? So we want the holes, we want the agent to learn that falling in the holes is a bad idea, right? But if our agent is estimating 0 it doesn't see any rewards, so it estimates 0 for episodes where it really doesn't get anywhere. That's exactly the same as falling in a hole. So it's not really discriminating between those two outcomes. So what can we do to help it learn? Well, one technique is a heuristic technique, and that's simply to modify the rewards that the agent sees. So when the agent falls in a hole, instead of giving it a reward of 0, we just give it a reward of -1. And that technique is called reward shaping. And we're going to find that it's going to help with this frozen lake environment. But in general, in more complex environments, you might need to experiment a bit to see what works best in your environment and for your reinforcement learning algorithm. What sort of reward shaping can help? Okay, so we're at the exercise now. So hopefully everybody's got some link they can click on. Maybe we can put it in the chat if they don't. But if we go to these links given on this slide, we should see an Open and Colab button that you can click, and that will open a Colab notebook that we can run through and experiment with some of these ideas.